going one way and like row 3, with all 3 shells, that's all they can have. But your nucleus is getting bigger as you go on because there's more protons, neutrons in there. There's more of a pull on those electrons because they can only go so far out, kind of thing.
Okay.
Is that right?
So the number of shells when you're going from left to right is the same. So there's only one thing that is affecting it, the nuclear charge. So forget about number of shells because that's constant. But these are the only things that are affecting the atomic size. So shells is out of the question. What effect will have the nuclear charge have on the size? When you're increasing the nuclear charge, what's happening to the pull? So you're increasing the number of electrons in the same shell, you're just increasing the pull. Because what this is forget about the shells, forget about the R. What's happening to these? The pull is getting stronger because when you're moving, say, from Na to Mg, the force of attraction between the nucleus and the electrons is increasing, because if this is the charge on the nucleus, this went from 11 to 12. So the force of attraction between any electron and the nucleus has increased. It's trying to pull more strongly. And that is why the size will, if the pull is getting stronger as you move from left to right, size will decrease. So whenever you go from left to right, the size is going to decrease. Right? This one is easy. Now, why this is easy? But the nuclear charge is still increasing, isn't it? So when you're going from, the nuclear charge went from 11 to 19 in the case of potassium. But we still think that it is increasing. Why?
More shells.
The more shells, the number of shells has a bigger, this is more important than this, because that has incremental increases. And this has a massive increase, like add a shell. So you're decreasing, so you are adding a shell and then decreasing, and then you're adding another shell. So this shell addition is a major thing. So when you're going from period to period, a shell is getting added, and that is massively more important. Okay? Okay. Okay, the next is also called IE for energy enthalpy. We'll understand the subtle differences between enthalpy and energy when we are studying thermodynamics, but for now, think that energy is equal to enthalpy. Okay? Does anyone have any idea what this is? What ionization? What should it mean? Something to do with? Something to do with ions. So you're making ions, first of all, okay? And you're making a positively charged ion. So the definition of ionization enthalpy is It's the amount of energy required to remove the outermost electron or a loosely bound electron from the outermost shell of an atom. Let me repeat that. Is the amount of energy required to remove a loosely bound electron from the outermost shell of an atom. Now remember, if this is the nucleus and if these are the shells, which is the most stable orbit?
The closest to
The innermost. So this is the most stable, lesser stable, lesser stable. Okay? Why?
Because there's more distance between
What's the mantra that I keep saying? That
increase in energy makes for unstable.
right. So which of these should have less energy? The closest has the least energy. The outermost has the max energy. So energy increases outward. This means that the outermost is the least stable. Okay? If I give you the job of removing an electron, which electron will you remove? Outermost, right? Because the base is the strongest here. The force is the strongest here. It would be very difficult to remove an electron from here. Not that it is impossible, but it is very difficult because this is the most stable. It's most closest and most strongly bound because R is the least. It's very close. Yes?
Okay, so for the noble gases, since their outermost shell is quote unquote like complete, and the further down you get, you have like more shells, is it still harder for them to hold on to those since they are stable? Or would it be easier because they have to put so much energy out to hold those outer electrons?
It's a good question. Can you repeat that once more for everyone to?
Okay, so the outermost is complete because the valence is in.
Yes.
And the further down you go, you have more shells.
Yes.
If it's already quote unquote stable,
Yes.
would it be harder for them to hold all those electrons because of so much energy they're putting out on the outermost shell?
So the question is whether as you go down a group, whether holding on to the outermost electron is difficult or not. What does common sense say? Will you be able to hold on? Is it easier to hold on to this electron or this electron?
The closest one.
So which one will be able to hold on to its electron the most? And this is radioactive, so let's not talk. And this will be the least. And that is why this is reactive. Because it's not able to hold on to its electron. So it can form anions, cations, whatever. It has the capability of doing both. Okay. Now, my job is to remove an electron from the outermost shell. And because it is the easiest, I will actually try and take an electron from the outermost. That makes more sense, and that's why the definition, the amount of energy required, and when I say required, can you say whether energy is getting in the system or getting out of the system? if something is releasing energy, if I say, for example, electron affinity is another thing, that is the amount of energy released when an electron in its gaseous state accepts an electron to form an anion. So if you have X, when it does this, an energy is released. So when I say energy is released, is it exothermic or endothermic? Does that make sense? When energy is released, if this thing is releasing energy, then what do you feel? If it's releasing energy, what do you feel? Is it?
Well, I guess if you have cold water in the bottle, then...
Say you have something in here, say
Oh, I see what you're saying.
hot water.
Hot. So then you feel... Yeah.
If this thing is releasing energy, you will feel what? You will feel the heat. So that thing is releasing energy. That thing's energy is decreasing. It is becoming more stable because it is releasing energy, and you are getting that heat. Okay? You're getting that energy as heat. So it's an exothermic process. So this thing is an exothermic process. On the opposite, ionization potential is an endothermic process because the energy is required to remove an electron. Now, the whole mechanism of removing the electrons, think about it like this. This thing has some energy, which is a negative. Let's assume this has negative 1 electron volt energy, or joule. This is not correct. The actual values are not correct. Okay, kilojoules, whatever. Let's assume that this has negative energy. And what does that negative energy mean? How can something have a negative energy? What does that mean? It is bound. This negative energy means this is bound. The moment this becomes zero energy, if that same electron is here, the energy is 0 joules, 0 kilojoules, whatever. Which has lesser energy? Negative -1 joule or 0 joules? Which has less energy? And it has negative energy. This thing has minus, say, 100 joules, because as you're moving closer to the nucleus, you are becoming more stable, isn't it? When you're becoming more stable, how do you become more stable? You drop your energy. So whatever that energy is, the energy is going to decrease. The flip side, whenever you go out, the energy is increasing. And we say that an electron is free from its nucleus when its energy becomes 0. It's a reference. Whenever we say that, this can also become positive, but when its energy is 0, it is very far from the nucleus, and we say that it has no control, that the electron is not being controlled by this. Okay? So our job is to free the electron, and when we free an electron, we call that ionization. So your job is to free that electron. How much energy will you give this electron to make it free? How much energy do you think you'll have to provide, required? How much energy you are going to provide this electron to make it free? 1 joule. Because this is negative, and you have to make it 0, just give 1 joule. Whatever that energy is. If the energy was 10, you give it, if the energy was minus 10, you give it a plus, you give that energy, and that energy becomes 0, and that is free. So that is the amount of energy that was required by the electron to make this an ion. So this is an endothermic process or an exothermic process?
If you're releasing the energy.
Are you releasing energy, or does the system need energy? It needs energy. It's not releasing energy.
So it's endothermic.
It's an endothermic process. So ionization energy is negative, and this is an endothermic process. Now let's assume you have removed this electron. Okay? Let's assume you have another electron. Now, what do you think? Because if you were in the same shell, the energies of all these, you could this will have -1, this will have -1, this will have -1, all of them will have -1. You can remove any one of them. But now, since you have already removed an electron, this thing has become an X plus. Now, what do you think? The energies of these things are going to increase or decrease? Are they going to be tighter or looser? They're going to be tighter. They're going to be held more. The electrons are going to be held more strongly by the nucleus. So, the second time you want to remove an electron, you need more energy. So, IE1 and IE2, which of them is bigger? 2. So IE2, both of them are endothermic, and IE2 is more than IE1, because now once the one electron is removed, you need more energy to pull that electron out. And the same, IE3, IE4, whatever. Okay? Think about electron affinity. Okay? Next time, because we are running out of time. I hope that you will be able to finish all of that, but if not, don't worry. I can extend it to next Thursday.
Do you have a chapter on your playlist?
Unfortunately for this, no. Yeah. Yeah. Okay.
I just want to know where you were when I was taking like regular Chem 1 and 2, and they just